So for the next part of our physics review, we're going to be looking at a pretty detailed look at the mechanics and the energies, because this one was all about energy and kinematics. So what we're looking at here is how energy shifts. There's potential energy as one of the types of mechanical energy. So the potential energy we are most focused on was the gravitational potential energy, MGH. There's also some discussion of chemical energy, but that was not quantified in physics. It was in chemistry, but not in the physics unit. There is also kinetic energy. When an object is in motion, we were calling it 1/2 mv squared. I say we're calling it that because that's the way Einstein found it. Einstein discovered there's a better equation than the one Newton used. The other form of kinetic energy, when you're looking at it on a subatomic level with vibrations, manifests as heat. So these are the key quantities that we were looking at and how energy moves from one spot to another. And energy moves by doing work. So the change in energy is the work done on an object, and that work done is a force acting parallel to the distance over which things are applied. So if you have a crate and you're pushing it, then the force is parallel to the direction of travel because you're pushing it along the floor. But if you have, say, a little red wagon and you're pulling that by the handle, well, the force you're applying is just that horizontal component, just what is parallel to the direction of travel. So all the force you're applying, some of it is done to lighten the load, lift it off the ground, reduce the friction, but that's not part of the work done. The work is the force times the distance over which it travels. Now a force is the mass times the acceleration of the object. And here we need to start drawing our arrows. We'll get into exactly why that is in a bit, but just a reminder, the arrows should be there. So F equals ma. If we're talking about the force of gravity, well, the acceleration due to gravity is a lowercase g. So our potential energy is really how much work gravity will do on an object if it falls through a height h. Right? The change in energy is force times distance. But when we're talking about the change in gravitational potential energy, the force applied is mg, and the distance traveled is the height h. So algebra really is a language. It's a way of expressing thoughts and ideas in written form. And as you learn to read the language of algebra, it'll be easier to keep track of how all these formulas fit together, because physics does have a lot of them. Now, as this falls, that mgh, that gravitational potential, is going to be turned into kinetic energy. Now, some of this will also depend on the path and distance traveled. One of the key differences and key concepts we dealt with was scalars versus vectors. So a scalar is a magnitude only, whereas the vector is the magnitude plus the direction. That is a very critical difference. So for example, let's take a look at distance versus displacement. So with a distance, all that matters is like the odometer reading in the car. If you drive this long and windy and snaky route, the distance you've traveled is the length all around this whole thing. So that's like the odometer reading in a car. Whereas the displacement, that's more like the targeting of a catapult. So if you've driven all this way, but then someone at the start of your journey has a catapult and they want to hit you with it, they don't need to know the distance you've traveled. They need to know your displacement and what your displacement is going to be when that projectile hits the ground, so that they can time it for the cannonball to land right there. So that is the difference between scalars and vectors. So another example of that is speed versus velocity. So the speed of something is just how fast it's going. So 100 kilometers an hour. The velocity is the direction of that travel. It doesn't feel that important at first because we're used to working just with speeds. But let's say you're in Edmonton and you want to go to Calgary. You want to figure out how long it'll take you to get there at 100 kilometers per hour. Well, if you stick to that 100 kilometer per hour or maybe 110 speed limit and you go south, it's going to be about 3 hours. But what if you don't go south? If you take your 100 kilometers an hour and instead go north and wrap around the North Pole, around the other side of the Earth, and then come up to Calgary from the south, this is not a 3-hour trip anymore. This is more like a 401-hour trip. And even that is assuming you're going at a uniform speed. You have to stop to fill up on gas, to sleep. You're probably going to need an oil change or two if you're going to be driving 40,000 kilometers around the planet. So, yeah, direction matters a lot when we're talking about these things. In some cases, that's more obvious than others, but it always, always matters. Now, another key point we deal with is the acceleration. That is the change in velocity of an object divided by its change in time. Now, this capital letter delta always means change in every time we see it anywhere in science. So if you have any variable here, call it x, that is going to be the final value of x minus the initial value of x. It is always final minus initial, no exceptions. So this change in v is our final velocity minus our initial velocity divided by the change in time. Quite often the change in time is just listed as t because we usually have our initial time set to 0. That's one of the gauge freedoms we have, which as a side effect leads to conservation of energy through something called Noether's theorem. This part is not actually in the curriculum, but Emmy Noether was an incredible mathematician. She worked in the field for about 3 decades and invented 3 fields of math in the process. When Einstein and 2 of his colleagues had been stuck on a math problem for 3 months, and Einstein found out that she was on campus, he went to her, left the problem with her. She not only figured out the answer that these guys could do that these guys couldn't figure out in 3 months, she invented a field of math to do it, and she did it the same day. So, very impressive woman, Emmy Noether. Noether's theorem says that we have a conservation law for every gauge freedom. We can choose when to start our timer in the lab. That means energy is conserved. We can choose where to put our meter sticks in the lab. That tells us momentum is conserved. We have the freedom to pick which direction is X, which direction is Y, which direction is Z. That leads to conservation of angular momentum. But that's time for another day. But for every freedom we have to decide where the zero is, we will have a conservation law. So these are a lot of the key points that we're going to be dealing with. And that will come up pretty heavily in the first part of Physics 20, as well as the first part of Physics 30. So the momentum and impulse unit is about 15% of Physics 30. It's more like 40% for the kinematics and dynamics together in Physics 20. But that all leads directly out of this component. So this will be the driving force in the first part of Physics 20.